I'm only whistling because I can't really talk super loudly if you guys don't mind. I'm going to try to get your attention just with a quick whistle letting you know that I'm ready to start talking anything. But you guys were, I heard a lot, at least quite a few of you trying to break down 60. The problem is, wait. Why were we even breaking down 60? If he had a perfect square, or if he was a perfect square, we could just answer it, right? What are those perfect squares from yesterday? What's the easiest one? What's the lowest one? The square root of 1, not 2. Square root of 1 is 1. What's the next one? Square root of
2.
We don't know that one. 4 is 2. What's the square root of? What's the next one? No? 9. What's the square root of 9? 3. What's the next one? Square root of 16 is 4. Okay, hold on. Some of us, the division and the square rooting is a little tricky. What's 1 times 1? What's 2 times 2? What's 3 times 3? A lot of you accidentally do less. What's 3 times 3? What's 4 times 4? Yeah, 4 times 4 is 16. What's 5 times 5?
5.
What's 6 times 6?
36.
What's 7 times 7?
29.
What's 8 times 8?
64.
What's 9 times 9?
81.
What's 10 times 10?
100.
These are the ones that I can do perfectly. We have 2 more, and they're the trickiest ones, I think, but maybe you disagree. 11 times 11? And what's 12 times 12? Okay. Is 68 one of those?
No.
So I would love to go hit the square root button on my calculator and be like, hey, what are you? But it's not going to be a perfect number. So the problem is, if it's not a perfect number, if it's not a perfect square, I should say, if it's not one of those, well, we got to go looking to see if there are any perfect squares in there. And some of you found one. If there was only one, what was the perfect square inside here? If you divided by 4, you would have seen there was a 17. Now maybe you wouldn't have seen this. But if you did divide by 4, if you realized there was a 4, the cool thing is from yesterday, we can change any multiplication. We can split up. Remember the beginning of the worksheet? Did you guys draw your arrows and say multiplication and division? That's checked. Those work. Addition and subtraction, those don't. Remember A and B, C and D? Those are not the same answers. They don't work. But E and F and G and H, those are the same answers. They do work. So I can take square root of 68. I can make it square root of 4 times square root of 17. What is the square root of 4? 2. So I can rewrite this as 2 radical 17. Now, what if you did this a different way? Did anybody take 68 and break it down to be 2 and 34?
Yeah.
Okay. So then you would have kept going, right? 2 goes into 34 how many times?
17.
Okay. So maybe you wouldn't have realized that it was a 4 and a 17, because some of you, this is like, oh, that's easy. I know that that's 2. But if you look at it like this, it's a little bit harder. But what if you then went ahead and said, okay, well, square root of that is, I can't do either of those. 2's not up there. 34's not up there. This is even worse. Except, can't I make a 2 times 2 a 2 squared? Or some of you thought of that as a 4. Either way, if you have square root of 4, you can simplify. Or if you have the square root of any squared, you can also simplify. You saw that before. Square roots are looking for roots of 2. Either way, you technically get to the exact same simplified radical. Now, a few of you are very dependent on your calculators because you're like, sometimes my calculator gives it to me. I understand that sometimes your calculator gives it to you, but then here's the question, what if I don't like calculators? Or at least the calculators that do it that way, or I come around and change all the modes before the quiz on Friday. Okay? We gotta think of, and we have to know this for that big old nasty formula that we saw yesterday. How to solve it on our own and not just have someone or something give it to us. Now, I do have over here the box on 98, because some of you do it the box way, not very many of you. But some of you have done the factoring tree also. But Jerry, yeah, you have a question. Can you just lean forward a little bit? Or does it get worse when you lean forward? Oh, it gets worse.
Yeah.
Just put your chair back a little bit. I think you should be out of it. Everest is coming back just a bit. Just didn't want your legs to get stuck. So 98. Some of you might have divided by 2, and if you divided by 2, you would have gotten 49. Oh, wait a minute. Did we mind 49? Yeah. Okay, so hold on. Why don't we just change the 98? There's a negative in front. But we can change the radical 98 to be instead a 2. And let's just go 49. We could have kept going and made it like 7 times 7 if you guys really wanted to. That's the proper way of prime factorization. We could have seen it that way too, and then we're done. But you could have also just said, hey, it's 2 and 49 with the negative in front. And then we could have said, which one do we know? So he gets outside of the radical. He breaks out. He breaks free. The 2 is stuck. The 2 is stuck. I heard 1 or 2 of you could switch them around and mix them up. So I wanted to make sure you know which one goes where. Max, go ahead.
So how do you know which one's outside of your?
Well, remember up here on the board?
Yeah.
The square root of 49 equals 7 without a square root.
Okay.
So then if you're actually taking a square root, his radical is gone. He's been broken free.
Okay.
But the other way of looking at it is instead of doing the 2 and 49, I could have also broken it down the longer way. And I could have had, it would have been 2 and then 7 squared, because 49 is 7 times 7. So the other way of looking at it is this guy's radical literally gets canceled.
Okay.
That one stays, the 2 is stuck, but this one gets removed.
Okay.
Does that kind of make sense?
Yeah.
And whichever one the radical gets removed, or whichever one you're taking the perfect square out, then that just gets written in front. Kind of cool.
Yeah, I got it.
All right, guys, I think we finished worksheet 9.1A, right? Okay, so with that, we are going to go ahead and peek at homework from last night in just a second. But I do want to go ahead and give you guys a moment, those of you that take notes, to write this down for today as I get the answers to 9.1A, the evens on the screen. But as I do that, I'm going to pass out 9.1B so you guys can see why I'm putting these notes up. And if you take notes on your worksheet, you can go ahead and start taking them on this worksheet itself. Because the first, let's see, 1, 2, 3, the first 3 problems need what's on the board. Yeah, this is 9.1. We're going to grade 9.1A homework in just a second. See if you guys had any questions. Come on, can you open this? Do you know how to kick this stand in and make it stay?
I'm going to do that.
Jerry, go ahead. Otherwise, our mouth will just get frustrating because it keeps on closing. Jerry, make sure you push it all the way towards the end before kicking it in. So those of you that take notes, you can be writing about what if it's a cube root. We only saw square roots last night. Those of you that take notes on the worksheet, now you have the worksheet. Armando, you can push your chair back if you want. I think that's okay. Andrew. Yeah. Better than I did. All right, so I'm pulling up the evens from last night. You guys are either looking at this to try to think about how could you tackle 1, 2, and 3, or you're writing down notes to get ready for today for us to do examples 1, 2, and 3. And you can have out a colored pen and your homework from last night. We're not collecting the homework today. I'm not checking it. Remember, I wait and check it all on the same day. So for us, we're doing 9.1A yesterday, 9.1B today. We're doing actually a 9.1C tomorrow. This is a weird 3-part section. So I'll be checking all of 9.1 on Thursday. The 3 worksheets and the 3 homeworks. You should have found a 16 when you broke it down, and the square root of 16 became a 4. Number 16, you should have found a 36 or a 6 squared. When you broke it down, square root of 36 is 6, and so that came in front. Number 18 was a little weird because there was a variable, but you were able to square root the 4 and square root the x squared. So you got the 2 and the x out. Number 22, okay, the top was stuck, but the bottom wasn't. Square root of 81 was 9. And on number 24, the 65 was stuck, but the 11 wasn't. It was square root of 121, which we didn't know. And then number 26 is 12 over k. Guys, I have the book open in the next tab, so does anybody need me to look at any of these in a little more detail? Were you able to break them down? Were you able to simplify? Were you able to deal with the variables and the constants? Any ones you got wrong or any ones you have questions on? All right, we'll see how that quiz goes on Friday and if you're able to get them right. Cool deal. Well, let's go ahead and come back to our worksheet then, 9.1b. Why do I have a cubed root up here? What do you guys see in those first few examples, 1, 2, and 3? Yep, there's a 3 in there. Now, the ones that we saw yesterday, there was no 2. Square roots don't have a 2 in there. We just finished numbers 5 and 6. Square roots are understood. If there's no number, it's called an index. From when we covered it last semester. There's no number in there. It's understood 2, looking for pairs, looking for perfect squares. But these ones, we got 3. Now hold on, I'm going to change colors. I'm not going to use blue. Let's use something else though. See if the green's coming. Does anybody know any perfect cubes? These are perfect squares. Square root of 1 is 1, square root of 4 is 2. Does anybody know what 1 cubed is? Yeah, 1 times 1 times 1. 1 cubed, which means the cube root of 1 is 1. 1 cubed is just 1. Does anybody know what 2 cubed is? Good. The cube root of, you guys did pretty good with that one last time. We're not going to do all of them because they get way too big. But does anybody know what 3 cubed is?
27.
27, nicely done. How about 4 cubed? People that know computers. The powers of 4 are really important in computers. That's why you have things like 256 and 512 and 1024, 2048. Maybe that doesn't mean much to you guys, but when little flash drives weren't able to hold very much, way before we were able to have like gigabytes on phones or on storage devices, there were megabytes, which are way smaller. And they would go by powers of 4 because that's how technology works, which is kind of crazy. Anybody know 5 cubed? 125. Andrew's rocking off you guys right now. The next one's a bit rougher. 6 cubed. 192, I think so. Are you doing a little 2-column multiplication? You don't even have a calculator. Because 6 cubed would be 36 times 6, right? 196. You were close. Because 36 times 6, you could always do a quick little. That'd be 36, carry the 3. Ooh, careful though. That's 18 plus 3. Ah, there we go. Are we starting to get a little bit high though? Yeah. We could go all the way to 10 cubed. That's the easiest probably, except for like 1. 1 cubed is 1. But 10 cubed, we just need to add another 0. So I guess that one's not too. Oh, that's a cube root. So I guess 10's not too bad. But the other one, 7 cubed, is going to be nasty. 8 cubed is going to be nasty. 9 cubed is going to be nasty. But 10 cubed is going to go ahead and just be 1,000. He's the easier one. Okay, do we have some perfect cubes? Yes. Are they as easy as perfect squares? No. So what we're looking for are powers of 3. Because 8 can be rewritten as 2 to the power of 3. 27 can be written as 3 to the power of 3. 64 can be written as 4 to the power of 3. We're looking for powers of 3. And if you remember from when we talked about it last time, I think I called them groups. Groups of 3. Let's go ahead and zoom in. Is 24 one of those? Okay, so 24 is not one of those nice ones. And P.S. a lot of your calculators don't really have a cubed root. They do like an X root and you can kind of try to put it in. It's not going to be as nice or pretty though. We have to break down 24. So what goes into 24, guys?
4, 2.
6 and, well, I heard the 4 and 6 one first, but yeah, you're right. It could be 4 and 6, could be 2 and 12. What goes into 4? What goes into 6? Is this going to be helpful? I see a group of 3, don't you?
Yeah.
Because another way of writing 24 could have been, ready? Could have been 8 times 3. And why would that have been nice? What do you see over there on the board? Do we know the cube root of 8?
No.
2.
It's 2. So we could actually say, oh, hey, got him. Well, I'm running into this problem, so I should probably come down. But that's only if you have those perfect cube roots memorized, which a lot of you don't. So what's another, and that's fine, you don't necessarily have to. What's another way of doing it? Well, we could have gone here and said, hey, I see that there's 2 times 2 times 2, which means a cube root of 2 to the power of 3 times a cube root of 3. So, Andrew, a cube root of 2 to the power of 3, guys, what happens if I have the groupings that match the root? Yeah, I'm allowed to cancel them out. Now, there is a snazzy way of doing it. It's technically rewriting the radical form that we talked about before, an exponential form. Once upon a time, we would rewrite them, and we could rewrite this to be a radical or a radical to be this. But either way, that becomes a 1 because those reduce. So you get a 2 to the power of 1 here, you get a 2 to the power of 1 there. Either way, we get a 2. And this guy, it's 3 to the 1. I got nothing. He can't be broken down anymore. So he's stuck underneath. Jeremy, what's up?
What do you,
Stop zipping. Yeah, no, that's okay. That was actually from an earlier section. It's actually from an earlier section. In that earlier section, we talked about radicals. And with radicals, we are reminded that whenever you have the nth root of anything to the nth power, because we can always rewrite that as a fraction. 5 over 5, 4 over 4, 3 over 3, 2 over 2, all reduce just to be 1. So it's kind of a shortcut to say, oh, you can just cancel out, and the radical and the power just get reduced to be what's underneath. Does that make sense? So a squared root, which doesn't really have a 2, is just a radical. A square root of something squared cancels. A cubed root of something cubed, a fourth root of something to the fourth. But this also lets us handle what if it was like a cubed root of a 6th power. I think maybe we could do something with that also. But we'll wait until we see it. Okay? That was number 1. Number 2, did anybody think about how we would break down 250? Gotta be kidding. We can go by 50s. Max, do you see anything else?
25.
Okay, so we could go by 50s. We could do 10 and 25s. To be honest, I also see that it's 125 times 2. I wonder why I'm thinking 125 times 2.
25 times 5.
But let's say that you didn't see that, and let's say that you went ahead and tried to cut it down by 50 and, what would that be? 5?
Yeah.
50 and 5, or 25 and 10, or 2 and 125, so many different ways. But if we did this, we would have kept going and said, okay, well 50 is not one of those, 5 is not one of those, let's keep going. So that'd be 5 and 10, and that'd be 5 and 2. Do you guys see how we have 5 times 5 times 5? So even if you didn't see it was 125 times 2, you still should have hopefully been able to see, hey, I have a cubed root of 5 cubed. I group all the like terms together. And then I have a cubed root of 2. And then what can I do with a cubed root of anything cubed? Remember, radicals are just looking for something raised to that power. So it just cancels out. So the 5 is out, the 5 is free, but yeah, what's with the 2? He's stuck. Dun, 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 dun. Can't come out, he's not cubed. And 2's not up here, right? I have 1, I have 8, I have 27. Yeah. I'll do this next one. Although this next one is a little bit funny unless you remember, oh hey, this is something I didn't show you guys yesterday. We talked about it, I just didn't show it to you. Remember how in the beginning of 9.1 worksheet, we saw how multiplication and division could be split up and they'd stay the same? But addition and subtraction could not be split up and stay the same. There was technically this page that I meant to show you and I just forgot. That said it's totally a property of radicals. That if you have multiplication, you can split up the radicals. If you have division, you can split up the radicals. I think I just helped out Caleb real quick. You can split out the radicals. That's going to be really helpful and really important for number 3. Do you guys see number 3? Isn't it one big fraction under a radical?
Yeah.
But we don't want to keep it one big fraction. Because if you look, who's on top of that big fraction in number 3 before I go to an A? Is he raised to any power at all? It definitely is not cubed. So he's not going to be able to come out at all. He's stuck. You can think he's still serving the sentence if that kind of helps. He's under the radical. He hasn't gotten more powers of A. Like unless he gets that cubed, he's stuck. But look at the denominator. If we can split this big radical up, which we totally can with division or multiplication, we can tackle that denominator. Which is good because it's not in simplest form if it has a fraction or a denominator with a radical. So let's go tackle that number 3. And then Kayla was asking for us to do the box method. So I'm going to go to a new page. And we have that cubed root of A over 27. I'm going to start by saying we're allowed to split up any radicals with division or with multiplication. We're allowed to split it up. Wait, 27, hold on. He's a good one, right? Who's the cube root of 27? Nice. But if you didn't see that, double check. Did I write down the problem right? I feel like that would be a negative.
There's a negative.
Thanks. That's sticky. A negative times a negative. If it was squared, it'd be a positive, right? But it's times another. That's okay, actually. I can pull that out. But, Kayla, here's what I would have done so it would work. I would have taken my negative 27, divided by 3, divided by 3, divided by 3. I'm in a bit of a pickle because I need them all to be the same, but I'm supposed to have a positive one, not a negative one. So I'm going to come back and say, okay, what if I divided by negative 3? That would have been a positive number. Divided by negative 3 would have been negative 3. Divided by negative 3 would have been a positive number. As soon as you get a positive 1, there's no other dividing to be done. Like you've gotten all the way down to the most basic number. And then at that point, you can just say, I know who negative 27 is. I know that the cubed root of negative 27 will be the cubed root of negative 3 to the power of 3. So I can just say negative 3 times negative 3 times negative 3. There's that power of 3 that I'm allowed to say, aha. So you can keep count of things with the boxes, or you can keep count of things with the factory trees. Now, hold on. Whoa. We need to finish this worksheet. What's the rest of the worksheet? Are there cube roots all over the place? Oh, nice. I think. Oh, number 6. But the rest of them are all just square roots, right? So hold on. There must be something else in this section because there is. My note-taking people. We need to keep on going to numbers 4, 5, and 6. And there is another cube root, that's true. But hold on, let's figure out the directions. Can you guys in the directions circle the word, what's the most important word in the directions?
Rationalize.
Good. Circle rationalize. That's what we need to talk about. So circle the word rationalize. That's the vocab term. If you're a highlighting person, highlight, decorate, whatever you want to do, whatever keeps you focused. I have a friend who, when she colors, she can hear a lot better than if she just like staring at you. She'd rather be coloring or drawing or something. Make sure you stay on track. Rationalize. If you look at numbers 4 and 5 and 6, all of them have radicals in the denominator. Do you see it? 4 and 5 and 6, all of them have radicals in the denominator. And we're not allowed to keep them down there. The simplest form, like we talked about yesterday. So rationalize is what to do when we have a radical stuck in a denominator. Makes sense. I see them. They're stuck. Okay? Now, here's the snazzy mathematical way of saying it. We're going to multiply by 1 creatively. We're going to multiply by 1 creatively. If the radical is alone in the denominator, we're going to multiply by 1 creatively. Now that sounds snazzy. It sounds good. Circle the word rational. If the radical is alone in the denominator, it's as easy as. Now, the radical's not alone. Well, do you guys see any ones where the denominator doesn't just have a radical, it has something extra? Where did those show up in the worksheet? Do you see any denominators, any bottoms of fractions, where it's not just a radical, where there's something extra outside the radical? No? Okay, look at number 11 and 12. Does that help? Look at number 11 and 12. Is there a radical down there in the bottom?
Yes.
Yes, but what else is there? There's a 4, there's a 5 that aren't in radicals. Remember, radicals are the square roots. So this first part is if the radical is alone. So if you want, you can say it's like numbers 4 through 10. Numbers 4 through 10, the radical's alone. For numbers 11 and 12, the radical's not alone. We're going to multiply to make the power match the root. What does that mean? Well, let me get some examples of it. We need to multiply to make the power match the root. Meaning, in number 4, when would the radical cancel out? How many 5s do I need? What power do I need the 5 to have to let it cancel? Well, no, 5 to the 1. This isn't a 1th root. What is it? It's a squared root. And a squared root needs the 5 to be squared. Do I have a 5 squared yet?
Yeah.
No, I only have 5 to the 1. So how many more 5s do I need? 1 more. Yeah, if I multiply top and bottom, I need the radical so that they join together. If there was no radical, they can't join together. But I just need 1 more 5. Because if I have 1 more 5, cool thing is fractions multiply across. So the 3 gets multiplied by the root 5. And what is 5 times 5? They both have radicals. They join together. They can separate apart. They can join together. Isn't my 5 squared now? Now some of you are like, it's 25. Duh. Okay, yeah, that works too. You can say this is square root of 25. Or you can say it's 5 squared. Either way, I'm trying to make the 5 be a power of 2. As soon as I get that, I can say, haha, square root of 25 or square root of 5 squared is just 5. It's my way of breaking them out of the radical person, if you want to think of it that way. You're finishing the sentence, you're paying the fine, you're doing whatever you need to do. You're meeting the condition to let him go free. And the way to meet the condition, the way to help him go free is to make the power match the root. I had 5 to the 1, I needed 5 squared, I needed 1 more, so I brought in 1 more. Now hold on, can we go to number 6 real quick? Go to number 6. I know it's weird, we're skipping. But go to number 6. We have 9 to the power of what underneath the cubed root?
3.
Okay, we need 3, but we only have 9 to the power of 1. So, how many more 9s do we need to make it match?
1, 2.
We need 2, because we need 9 to the power of 3. So couldn't I multiply this guy by the cubed root of 9 squared? The cubed root of 9 squared. I'm going to go ahead and show it down here because it got a little small. 5 times the cubed root of 9 squared. Because what would happen if I did 9 squared times 9? I'd have the cubed root of 9 cubed. And then, now I made the powers match. Remember, when I make the powers match, the radical goes away, the guy goes free. Now, just a few of you, there is another way of writing this answer. Because 9 squared is kind of rough. You could have written that with an 81 under there. But to be honest, there was even a better way of writing this. We wouldn't just leave it 9 squared, we'd make it 81. There's even a better way of writing this, though. And the better way of writing this is actually like, wait a minute, isn't 9 3 times 3?
Yeah.
Oh, I could have done this another way. I could have, instead of thinking about it as 9, I could have thought about this problem instead as, wait a minute, I could have made this 5 over, maybe I should have broken down 9 to see that he's actually 3 squared. If I went down to 3's, how many more 3's would I need to make it match? I already have 2. I need it to match the power of 3. How many more do I need? Just 1. So I would just, now remember, I have to keep the radical the same so that they go in the same grouping. The radical is kind of like if you go to pay a bill, you need the person that you're paying to know that it's for you, so it goes into your account. I need them to match so they go together. I could have done it this way also, and actually it would have been a lot easier because the numbers would have been a lot smaller. But that one we would have had to break down. Now we have 3 squared times 3 to the 1. Now I have 3 cubed altogether. And I can go ahead and say that this is the simplest, best answer. So I'm still going to put over here to the side. If you can, break it down first. That 9 could have been broken down to be a 3. And even though we're not wrong over here, this one would be the simplest one. Now guys, we're not going to finish number 5 today. We're going to actually go to the next section so you guys can see what the next section looks like. But can you just help me out as to what you think we would multiply top and bottom by? Knowing they both have to have a square root, because I need these guys to join together. But what do you think I would need to put in there in order to make it simple? Good, I need a 7, because I need the 7 to be squared. But what else do I need to get free of that radical? The 1 actually isn't under a radical, so he's okay, but I need the n to get free. And multiplying by 1 creatively means we multiply the top and the bottom by the exact same thing. The top and the bottom by the exact same thing. Now this 1 has to stay outside because he's not under a radical. So they don't get to join together. But that's okay because 1 times anything is itself. But down here on the bottom we would have a 49, 7 times 7, n squared. We could have also written 7 squared. But either way, I know the square root of 49 and I know the square root of n squared. Went ahead and wrote that 49, so some of your brains are going to think 49. The square root of 49 is 7. The square root of n squared is n. And on top, I have that 7n. Remember, we're trying to get simplest form. And simplest form says no more radicals in the denominator. No more radicals in the denominator. But we wanted to get to that last section, and so let's see what's going on in that last section. We're not going to get to number 11 and 12 today, guys, but that's totally okay, because I think that's at the very end of homework. We'll get to the ones before 11 and 12, and then tomorrow we'll talk about what about those tricky 11 and 12 ones. Wait, hold on. I think we're just supposed to simplify, right? Doesn't this look kind of like 4 and 5? What do you think we should multiply this guy? We're not even going to finish it. Just what would I multiply by? Yeah, root 5 over. That's easy. What about this guy? What do you think? Root W, yeah, over. Root W, yeah. We'd have to simplify, but that would get us what we want. How about number 9? What happens if we have a constant and a variable? Yeah, good, just like that 7n a second ago. We would have to simplify, but you guys are doing great. Ooh, what about number 10? We're not doing 11 and 12. We're just going to save those for tomorrow. Remember, 10. You guys realize we could break this up to be root 2 times root z squared all over root 7? The z is not a problem, but what is? So what would I multiply top and bottom by? Got it. Bye guys, I'll see you later. Homework's on the side, but it's also here. So take a picture. Sorry. A picture on the way out the door. Remember, all of 9-1 ABC.
So tired.
Seconds on the left. All of 9-1 ABC to 100. Calculators and this other